for having me. I'm really happy to be here virtually. Interaction and NLP has been kind of close to my heart. I've been thinking about it a lot through our previous work on interactive semantic parsing and dialogue. And more recently, we've been working with Dorsa, who spoke earlier today about language and robotics application. But increasingly, as we see these larger and larger deep learning models become kind of the focus of NLP, but also beyond that, I've been thinking a lot more about these models and how to interact with them in terms of how to control them and how to interpret them. And what do we have to do to design different types of models to facilitate that? So that's going to be the topic of my talk today. So we all know that deep learning is everywhere and it's all around us, and it produces models that look like this. They are large, powerful, but really hard to control and interpret. So let's take an example. So suppose you're trying to use deep learning to analyze knee x-rays to predict the severity of arthritis. So textbooks, ConfNets will work pretty well off the shelf on such as these tasks. But if you wanted to know why did the model make a certain prediction, it's really hard to get a straight answer. And what if you wanted to intervene? And there's not really a good hook into this model. So let's take a second example, text generation. We now have these huge language models such as GPT-2 or GPT-3 that are able to produce really stunningly fluent prose, but they're known to lie. It's what Stephen Colbert would call truthy, something that looks true, but is actually not necessarily true. And so how could we then make them generate text that's more consistent with the facts? In other words, how can we steer these language models? So the talk is going to be divided into two parts, concept bottleneck models, which will talk about how we can change the models to kind of allow humans to intervene and interact with them, and prefix tuning, which is a more which appeared at this ACL on how to steer language models to produce good generation. So let me begin with the first one. So this is joint work with Panwei, Tal, Yushan, Steve, Emma, and Bean. This appeared at ICML last year. Let's go back to our example of predicting arthritis severity. So suppose the model predicts no arthritis. So if the doctor wants to come and ask why, in other words, interact with the model, well, the model doesn't talk. So maybe you could try to read its brainwaves, which is kind of akin to like probing or other work on interpretability. But it's not clear that this post hoc interpretability actually produces meaningful answers. But if you had a human, they can offer an explanation. The human might say, oh, I didn't see any bone spurs. That's why I think there's no arthritis. And ideally, the doctor would be able to have a dialogue and say, well, isn't that a bone spur over here? And then the human would say, oh, okay, all right, you're right. Maybe I can update my beliefs and try to make a better prediction. So what we have done here is a sort of test time intervention. We said, if this high-level concept equals a new value, what would the prediction be? And the nice thing about humans is we have the ability to use language to access these high-level concepts, whereas end-to-end deep network, all you have is the input, and then you have a bunch of layers in between, and you have the output, but there's not really a hook into the model. So the closest work that in this space is kind of the work on interpretability, which is there's a rich literature, network dissection, salience maps, and all the huge Bertology work that's happening in NLP. And most of this assumes your favorite network, whatever the architecture is trained, and then you try to read out any concept of interest. But the problem with that is that there's no guarantee that what is read out is actually the reason why the model is making a prediction. So what we're going to do in this work is to think about how do we create constructive explanations. And this is in turn going to help us have a meaningful way of interacting with these models. So we're going to revisit this old idea of learning with concepts. So before deep learning took over everything, we had some work in computer vision where people tried to break up the problem into predicting various types of attributes and using those attributes to predict the final label. And often these methods were interpretable, but they weren't as accurate. It was subsumed by deep learning. So in this paper, we revisit this idea and kind of resurrect it and say, can we actually make this work and not compromise accuracy, but still get interpretability? And so we have this very simple idea of a concept bottleneck model, which is, I think, a nice way to think about how to do this. So the idea is you take your favorite deep learning architecture, let's say a ResNet, and you resize one of the intermediate layers, usually the ones that are closer to end, to exactly the number of concepts you're interested in using to explain. So in this example, the concept might be various types of properties of that the doctor would be defined by the doctor. Here's another example. If you're trying to predict the bird species given a bird in this Caltech birds data set, then the concept might be things like wing color or beak length. So given this setup, it seems kind of straightforward. You have a set of inputs. We assume that each input example is labeled with the concepts, and then you have also the output label. And then you have to train. So now here is the subtlety, why this is actually it's not kind of a simple question. There are many ways to train. So let's start with the baseline. The baseline is you ignore the concepts and you train a standard model end to end. There should be an argument over here. So you find the classifier that minimizes, in the case of regression, the minimum squared loss. So now the simplest way to perhaps incorporate the concept C is what I call independent training. So you take XC pairs and you train a model. And then you take CY pairs, you train a model, and the training is independent. Now, the problem with independent training is that there's the kind of domain shift problem. So at test time, what you're going to do is you predict with the first model, G, but then the outputs of G are not the true concept, they're the predicted concepts, but the following model assumes true concepts. So there's a mismatch. So to address that mismatch, we can do sequential training, where you first train the first layer to predict the concepts, and then you use the predicted concepts to predict the final label. Now, there's another thing we can do, which I think kind of subsumes many of the formats, is you can do joint training. So you have these two objectives, the C to Y layer and the X to C layer, and you put a lambda term, which allows you to weigh the trade-off between predicting the concepts accurately and predicting the final target accurately. So if C goes to 0, then you get standard training. If C goes to infinity, you get sequential training because it's really paying attention to getting the concept labels first. So how well does this do? So this table shows across all the different methods, we have X-rays and birds, the data sets, and we see several things. First of all, on the X-ray data set, there's not much separation between the different types of concept bottleneck models. And they're pretty comparable to actually doing standard training. So here's a case where you might imagine you can get the similar accuracy, but not lose on interpretability. And for the birds data set, it's a little bit more nuanced. We see that there is a difference between joint training and independent versus sequential training. But if you do joint training, you can have your concept bottleneck model not lose on concept accuracy and still be comparable, a little bit worse than standard training. So remember, the premise is that standard training is kind of what works best because it's end-to-end. It can just fit everything, including spurious correlations. Introducing concepts, it gives you a structure, but it often can be limiting. And we show that it seems at the moment that you can actually get most of the gains by having these concept bottleneck models as opposed to completely end-to-end training. There is a subtlety here, which I'll get back to later, and has to do when we start doing interaction. So remember, we talked about post hoc explanations. So if you take a standard model and then after the fact, you go and you try to probe for these concepts, we find that the concept accuracy is much worse than if you do concept bottleneck models. So the point here is that post hoc explanations don't just magically produce the concept you desire. There's no mind reading. you have to kind of bake them in if you care about these concepts as the way that the model should be, what the model should be using to predict the right answer. So because you're predicting Y through these concepts, you might hope that you're more robust to domain shift. So we did a simple experiment on a semi-synthetic data set to just kind of prove out as a proof of concept. So we take the CalSec bird data set, and we constructed this other data set where at training time, birds are placed on different backgrounds than they are at test time. So now there's this shift in background. And if you don't use concept bottleneck models, you see that you do worse than if you use concept bottleneck models. So the idea here is that your models can be more robust if the concepts are less prone to shift. So now let's get to the interaction part, which is the theme of this workshop. So remember, the concept bottleneck models give you this intermediate layer, which is a set of real numbers where each number corresponds to some concept. You can intuitively think about the probability of that concept being there, if you like. And this tells you what the model is thinking, which also means you can go and intervene. So if the doctor says, no, I actually think there is a bone spur, then the doctor can just go set that the value to 1 and then run the model forward using an intervention. And in this case, it will predict the right answer. So whereas before you just had uninterpretable hidden units, but now the hidden units have meaning, which is why you can do this intervention. So we simulated this interactive setting using kind of an oracle. And this plot shows as you intervene on more and more concepts. So at test time, you remember we're predicting, the model first predicts concepts, which could be correct or incorrect. And then we're going to go through and we're going to replace it with ground truth concepts, thinking, simulating an ideal doctor who knows the correct answer. And we see that if you do independent training using concept bottleneck model, then sure enough, the error rate goes down, which is expected because now you're just using more and more correct concepts. One thing that's interesting to note is that if you do joint training even though you seem to get good high concept accuracy, intervention doesn't actually work that well. And whereas if you kind of have some sort of intermediate regime where you have sequential, if you train kind of sequentially, it can kind of be somewhere in between. So the punchline here is that concept bottleneck models allow for this test time intervention, which is, I think, a really interesting, unique property to have. And then independent models provide better test time control because there's less distribution shift. It's trained on the correct labels, and at test time, you're going to put in correct labels, then that provides a better match. Okay, so just to summarize concept bottleneck models, we show that at least on these two applications, we were able to get comparable accuracy to standard end-to-end training. And we're offering constructive explanations. I want to stress how important it is for the explanations, which is one way of interacting with the humans, to be actually constructive. Otherwise, the model can just say one thing and do something else. And finally, one cool thing about these concept models is that it provides these test time interventions. So you can go and you can talk and have a dialogue with this model. Now, there's some open questions. We demonstrated this idea for 2 data sets. What else could we do? Can we relax the bottleneck assumption? There are definitely data sets, such as, let's say, recognizing whether something is, let's say face recognition, if you were to do such a thing, to, I don't know why images some face. There's just some maybe not intermediate concepts that could help me tell that. So how can we relax this bottleneck assumption, but still manage the degradation and explainability? And finally, one thing that we've been actually exploring, which I'm not, we don't have, it's not published, so I don't have slides on this yet, is exploring the idea of using language, going back to the idea of language being as a kind of a concept bottleneck layer itself, because language is much more expressive than, say, a predefined set of concepts. So we're kind of exploring this within the context of large language models right now. Okay, so let me move on to the second part of the talk, which is going to be about prefix tuning. So this is a joint work with my student, Lisa, and this was published at ACL this year. So let's go to the task of table to text. So you're given a structured table of facts, and you're asked to produce a fluent English sentence that describes the semantics of what's in the table. So these days, probably the best way to do that is you go online, you download the largest model that you can find, and then you fine-tune the model on task-specific data. So one problem with fine-tuning is that it can be expensive. So GPT-2 has 1.5 billion parameters, and if you were fine-tuning a model, then it touches all the parameters, and then you just get a copy of 1.5 billion. And if you, for every task, you would have to store 1.5 billion parameters, which seems kind of inefficient. So the question is, do you really need all those parameters there? So there's been recent work exploring this idea of lightweight fine-tuning. Maybe you don't need to fine-tune all the parameters. The easiest thing you can think of is just fine-tune the top two layers. And we show later that this actually hurts performance quite a bit. So you can't just get away with just fine-tuning the top two layers. Adapter tuning is this kind of a nice idea, which showed that you can actually get pretty good performance fine-tuning only 3% of parameters. And now the question is, can you go even lower than 3? What if happens if you fine-tune 0.1% of parameters? So in the extreme limit, we have, I would say we have in-context learning, which is a capability that GPT-3 has. So the idea of in-context learning is you capture your task via some instruction, you give a set of a very few examples, and then you provide the input, and you concatenate those into an input into the language model, and the language model produces the answer, or you hope it produces the answer. So this is a really kind of cool way to do learning. The disadvantage is that you can only train on a few examples, the number of so many examples that can fit into the window size of your transformer. And it only works well with huge models like GPT-3. Like GPT-2 can't really do it. So, but nonetheless, we can use prompting or in-context learning as a motivation for what we're going to develop here. So let's think about prompting. So what is prompting? The prompting is the idea that you're going to solve some task from mapping inputs to outputs. For example, predicting the capital of a country. So the country is the input and the capital is output. So you're going to construct some prefix, a global prefix, that you're going to stick in front of the input. So maybe in this case, the capital of France is. And then you're going to feed this into a language model, and you hope that it produces the output. So you're kind of priming this language model to do something. And then for our table to text task, we would try something, it's a bit more complicated. You can serialize the table into a string, and maybe you can put describe or something to put as a prefix and hope that the model can output the right natural language sentence. But is a prefix powerful enough? And if so, how do we even find one? And so the way to think about it in terms of this kind of metaphor here is that you have this language model, you can't really control it, but what you get to do is you get to dangle all sorts of treats in front of it, which is a prefix. And hopefully by dangling treats in front of it, you can get it to do various things. And there's this idea called autoprompt recently that does a discrete search over prefixes. They do it for sentiment classification, not generation. So there's some work that, and there's actually quite a bit of work that revolves around somehow optimizing these prefixes to get the model to do various tasks. So we're going to take another route, which is going to be more based on closer to fine-tuning. So remember, prompting was just inspiration. Now we're going to go back to fine tuning and see how we can incorporate that intuition. So here's a little bit of notation just to set the stage. So we have X, which is the input, and Y, which is the output. We're going to call Z the concatenation of the input and output. And an autoregressive language model like GPT-2 or 3 computes a sequence of hidden states where I'm using HI to denote the stacked up version of the hidden representation across all the layers. So the number of layers L times the dimensionality of each hidden layer. And that's a model. And when we fine tune, we just fine tune all the parameters of the language model. Now, the key idea behind prefix tuning, and this is a key slide that actually describes what we're doing here, is intuitively, you can think about it as prepending these virtual tokens. Now, these are not going to be tokens, so it might be a little bit confusing, but we can maybe, if it might be helpful intuitively to think about them as virtual tokens. So this is a prefix. And the same thing, we're going to just autoregressively compute a hidden vector given the past. But the key thing is that for this prefix, instead of running it through this recurrence, we're just going to have free parameters that we're going to backprop. So we get to backprop directly through H1 and H2, essentially. And here we're going to distinguish the parameters and call them theta, but they're effectively H1 and H2. So now we have a much smaller set of tunable parameters. Instead of the whole transformer, we just have this prefix. So that's the idea. And I also should mention that since this work, we worked on this work, there was actually a bunch of other papers that have come out, some concurrently, p-tuning, prompt tuning, and many more. I think I'm apologies to if I'm omitting something. And I guess all of them start with P, so we can call them P star tuning, I guess, methods if you want. So how does this work? So we ran on 3 data sets. The first, 4 data sets. The first data set is E2E, where the goal is to take a restaurant review, a structured representation of restaurant review, and generate the review. And on this plot, I'm showing the percentage of tunable parameters versus BLEU score. So if we start here, this is full fine tuning. We're tuning all 100% of the parameters, and we're getting some BLEU score. If you fine tune the top 2 layers, your accuracy drops a little bit, but it's not too bad. You can, if you do adaptive tuning with 3% of the parameters, you can actually do a bit better, which is somewhat surprising. But if adaptive tuning, if you really are stingy and give it only 0.1% of a budget, then accuracy drops or BLEU score drops. Prefix tuning actually works surprisingly well here. At 0.1% of the tunable parameters, we're actually able to get even better accuracy than full fine tuning, which was actually surprising to us. We were just hoping to match fine tuning, but actually here we're getting something even better. WebNLG, the task is given a structured set of entries about some entities, generate some sentences describing them. Fine tuning, if you fine tune the top 2 layers now, the accuracy drops quite a bit. Adaptive tuning recuperates, but notice that even at 3%, I think this is a typo, that should be 3%. Even at 3%, this is still lagging behind full fine tuning. Whereas prefix tuning is a little bit worse, but more comparable to fine tuning on this data set at 0.1% of the parameters. So which is pretty good. You're only losing a little bit for only storing or tuning rather 0.1% of the parameters. I should say that you still have to maintain the parameters of the whole language model. So this isn't exactly distillation. So Dart is a similar story. Fine tuning does pretty bad if you drop just everything but the first. If you don't fine tune other things besides the top 2 layers, adaptive tuning isn't able to keep up, whereas prefix tuning does pretty well. On summarization, now we have to, I'm going to skip over the details, but we have to modify the model to support this encoder-decoder approach, but you can see the paper for details. For summarization, now here, summarization is a more complicated task. The sequences are longer. It's just more lexical variation. here we weren't able to get as strong results as fine-tuning. So not bad, given that we're only doing 2% of the parameters, but we weren't able to keep up and definitely not exceed the performance of fine-tuning on these summarization tasks. So one cool thing about prefix tuning is that it can do extrapolation. So extrapolation is what happens when you train on a set of categories, examples from a set of categories, and you test on unseen categories. So here, there is some overlap between some of the relations between let's say birthplace, but other relations are distinct. Now, all of these are rendered via natural language. So the language model, even though it hasn't seen any of these categories, should still know something about it. So if you train on a disjoint set of categories, then you test on, we see something kind of interesting, which is that adapter tuning and prefix tuning, which are the methods that preserve the LM of as much as possible, works a lot better than the ones that full fine-tuning or only fine-tuning a subset of the parameters, which destroys, kind of destructively, just modifies all the parameters of the LM. So we have this intuition that preserving the LM is actually important for extrapolation, which is actually a really important thing to ask our models to be able to do. And a related paper from ICML that we had was composed fine-tuning, which strengthens this evidence that preserving the language model is good and has some theory in there as well. So just a quick ablation. One thing I should note is that we call them virtual tokens, but they're really not tokens at all. They're just full-fledged free parameters, and they're parameters that run across the entire depth of the network. So if we treated them more as tokens, for only touching the embedding layer, then actually accuracy drops a lot. And this shows that you really need the kind of the power of the full depth to get it. And one other thing is that optimization over discrete prefix is even less expressive, because with embedding, you're basically making up words because you get to assign whatever word vector you want for these kind of placeholder tokens. Whereas prefix tuning, they're not even words at all or made up words. They're just full-fledged parameters. So, but the point of this is that at least for these tasks, you need the freedom, or we show that you need the freedom to tune each layer, not just the token layer. So to summarize so far, we introduced this idea of prefix tuning, and it captures it's kind of a marriage of two ideas. The idea of fine-tuning and more generally lightweight fine-tuning, where you're modifying the parameters via backpropagation, and prompting, which is really about conditioning. You have these language models, and one way to kind of modify them is to condition on inputs. Another way to modify them is to backprop. So there's kind of forward and backward ways of modifying, and prefix tuning can be viewed as kind of a synthesis of these two ideas. We showed pretty good performance by tuning only 0.1% of the parameters. And one interesting thing is that it extrapolates out of domain. Of course, there's many open problems. How can you close this performance gap? Why does this work? Is it because of preserving the LM? And I think really this opens up a whole host of new strategies for what is the right way to lightweight fine-tune. And what's clear here is that it's not really the number of parameters. It's judiciously figuring out which parameters and how to parameterize the model so that it can preserve the LM and give you good results and even good extrapolation. Okay, so I will quickly wrap up here. So we saw two works which revolved around this idea of we have these deep learning models, which are by default fairly black box and uninterpretable. And the question is, how do we interact with them? And we showed first that with concept bottleneck models, we can kind of do surgery and carve out a hidden layer and call that a concept bottleneck layer. So it provides a hook into the model so that you can interact with it. And then with prefix tuning, we're leaving much of the deep learning model as is, but we're dangling this carrot out to help guide the model. So both of these projects are kind of trying to work in this kind of prevailing ecosystem of how you want to leverage these deep learning models, but you still want some amount of interactivity, and which in this context of this is interpretability and controllability. And there's obviously many more directions that we like to pursue, incorporating more language, and there's also a lot of related work that's coming online. Okay, so with that, I'll conclude. Thanks everyone for your attention, and I'll take any questions. Yeah, thanks for the question. This has been exactly kind of the right question to be asking for these models. I mean, again, this is a kind of a proof of concept, and we honestly struggle to find cases where broadly you need several things. You need it to be the case that your task is decomposable in this way, and you also need it to be the case that you need to be able to, at least in this case, annotate them. So for the annotation perspective, actually, I think you can get away with much fewer. We haven't really explored this, but you can think about annotating only a subset, maybe the ones that are relevant, maybe use active learning, which I think actually is a really, I know that active learning sometimes doesn't quite deliver as much as you would hope, but I think actually in these contexts of where we have maybe a large number of redundant concepts, it can actually give you gains, much better gains than just trying to annotate all of them. Now, for the first point is how widespread this is. I think it's for some very kind of reactive tasks. I think maybe not so much, but I also think that there are opportunities with these that in tasks which we maybe haven't discovered or thought about. And I also like to think about this concept of models as more pushing even more in a kind of interactive process, right? I think if you go and sit down, like NLP researchers, we're used to having like these data sets, someone else decides the task. But in practice, often you don't have the task in mind. You're just like saying, okay, have maybe an idea of what I want to do. And then you can maybe try to write something that produces some output, and then you can interactively go and you select, maybe add concepts interactively. So actually the concept of models was based on this Flock, which is this paper out by Michael Bernstein's group in HCI a few years ago, where they actually had crowd workers provide concepts. And so I would think about these models as perhaps good for if you really want to embrace the interaction and push on these kind of high-level tasks where you, by construction, want the provenance there, and you don't just care about the end accuracy. Yeah, that's a really interesting idea and something we've explored a little bit. I really like this idea of kind of contrastive or minimal pairs, if you're more of a, I guess, a linguist. And in some sense, if the question is like, where do these concepts come from? They have to come from humans, and it's, if you ask a human like come up with a concept, it has to be grounded somehow. And I think contrastive pairs is a good way for showing someone, and helping people understand these concepts, because I think it relates a little bit to teaching as well. Like if you want to teach someone a concept, you show kind of minimal pairs that illustrate. So that's something definitely would be interesting to explore. Oh yeah, that's a good question. So sorry, you didn't make it clear that the 2 is just illustrative here. 2 does actually work for some of these table to text generation terms. For summarization, we need many more, like up to 100 even. We did experiment with this. There, as you might imagine, there's this kind of a sweet spot where if you have too many, then you start overfitting. If you have too few, you're not expressive. It's not super sensitive. So you kind of just try to minimize the number of the prefix length. Yeah. Yeah. So regarding how to use concepts for robustness, I mean, I think the conceptual story is, you know, clear in terms of concepts are kind of doing the right thing, and if you're doing the right thing, you're more robust. In practice, it is, I think, as you might be kind of getting at, is a little bit harder. We know that there's a kind of reason why deep learning took off, right? In NLP before, people said, hey, let's use parse trees. This is like kind of the right way to construct the syntax and the semantics, and then you do all this stuff. And then without realizing that a lot of the time you're dropping a lot of useful information on the floor for your downstream tasks. So it's very lossy. So that's the main problem with even domain experts, is that they think that the right answer is something, and but actually, it's really not, because of, I guess, humans are valuable. So I think it's a little bit of a double-edged sword. It gives you, if you're really sure, it's a good way to incorporate prior knowledge, but I wouldn't, definitely not advocate for, oh, we must do things this way, and we're back to kind of consulting experts. But because there is, but I think it gives you maybe some useful contrast, because we already know how to train deep learning models. So let's train it and see what happens. We can also introduce these concepts, and we can measure, like, are they getting the same accuracy? If the deep learning model is like way better, getting way better accuracy, it either means that, well, actually maybe domain experts didn't know it as much as they did, or the data set just has tons of spurious correlations, which is probably actually going to be more often the case. So it gives you another tool, and there's also ways to kind of blend concept bottleneck models with deep learning. You can like put a shortcut, like kind of that goes past the concept bottleneck models. But of course, then you lose the cleanliness of the interpretability and the controllability. So you have to be a little bit careful if you do that. But robustness, yeah, going back to your maybe original question, is we demonstrated on this some fairly kind of, I would say, synthetic setup, where we just like have the train and test be just different backgrounds with the same birds, right? In the real world, there are all sorts of robustness problems, which some of them have nothing to do with your concepts. So I wouldn't, definitely not say it solves all robustness problems, but I think it can help, especially if your concepts are more stable to shift. That's a good question. That's a good point. So certainly, these virtual tokens, I kind of hesitate to use them, because they're not really virtual tokens. They're even less interpretable than virtual tokens. I wouldn't necessarily say, though, that the prefix is less interpretable than, certainly no, I would say it's not necessarily less interpretable than discrete tokens, because sometimes if you really optimize for discrete tokens, you're just going to get some random words, and it's not actually clear why these, I mean, because of the presence of adversarial examples and all that, it's not clear whether these words actually have anything to do with anything. So it just almost feels like sometimes a poor man's optimization. Now, of course, discrete tokens are useful when the expert comes in and is actually going to write a description of a task. But the description is not going to be optimized for the task, because it's not based on example, it's based on what the expert thinks. I do think that prompting seems, I mean, already we see a lot of follow-up work on kind of using prompting, and it seems very promising. I do think that we're probably missing, it's only one example. There's, I think, nothing sacred about prompting. I think we're perhaps, I would like to think that there was a kind of a more general story about inductive bias and kind of efficiency here, because, like I alluded to in the talk, there's many parameters, subsets of parameters you can tune. The design space is huge. Prompting is just, we saw GPT-3 and it's like, oh, okay, that would be a nice idea. But there's probably many ideas that everyone here in the room can come up with. And it'd be interesting to try them and see if there's any more generalizable principles here. I mean, you can do kind of whatever you want. You can set it to 0 or 1, or if you're not sure, set it to 0.5. One was, example. Um, I think it boils down to kind of the meaningfulness of the hidden layer. There's also like a kind of subtlety when you not do regression and you do classification. You have to do it at not the probabilities, but the kind of the logits. So which I kind of swept under the rug. So it's a little bit less straightforward than that. I mean, the other thing to worry about is that the concepts, to the extent that they're kind of factorized, then maybe you can just tweak them one at a time. But if the concepts are somehow correlated, it doesn't really make sense to just change one of them. You have to kind of change them in a coordinated way. And kind of a trivial example of this is that actually for the birds, most of the concepts are like kind of indicator one-hot representations of like multinomial variables. Like a bird could wing is black or red or blue, and if you change it, you kind of have to change two variables. But yeah, it definitely requires some care in intervening. Oh yeah, so the human aspect is interesting. Let me comment about that. So the human's job is to provide annotations of concepts. And actually, from that perspective, this concept bottleneck models is actually a strength for some settings, right? So for example, this bird classification, I have actually no idea what any of the birds, except for maybe robin. I think I can recognize a robin is, but I could sure tell you the color of the beak, and I can tell you if it has a long, a neck or not. So by decomposing, you can actually increase greater accessibility and more intuitiveness to humans. And now provided that I don't actually know too much about bird classification, but it seems like these characteristics are sufficient to produce the final label, which actually kind of decomposes the problem into something that maybe an average person can do versus domain experts, where they actually need to think about the birds species. So the humans aren't actually trying to do this weighting thing. The weights of the concept should be learned from data. They're just providing identities of the concepts for individual examples. Yeah, that's a good question. I mean, I was going to say, yeah, the obvious thing is just do like a gradient update on the new example. Yeah, what else could you do besides that? Because the supervision of this intervention is in some sense specific to this example. And so it's unclear how you would necessarily, generalize it. Now, I think that maybe I haven't thought this through, but just kind of riffing a little bit. Maybe because we factorize the problem a little bit, maybe people can actually provide more general guidance, like usually read to can give you kind of general rules on the concepts. Let's say, like, no, you keep on making this mistake about when you see this, whenever there's a black beak, then the web. I don't know. This is clearly out of my depth, but so I could see a case for maybe doing something other than just like training on the example, provided there's a mechanism for the humans to interact on kind of a type level rather than an instance level. Yeah, thanks for bringing that up. I mean, one thing that we don't do, which would actually would be a great kind of addition to concept bottleneck models, is that kind of localize in the actual image. This is like holistic. Here's image, just predict red beak. I don't know where the red beak is, but you could, I think, even kind of increase the interpretability and probably would help with generalization to be able to localize different concepts in the image, which is something we haven't done yet. Now you can probably, get there's all this work on continual learning that we can probably bring to bear on this, kind of like a replay buffer.